welcome to everybody. My name is Jeffrey West, and I'm on the faculty of the Santa Fe Institute, and it's my real honor and distinction to be able to introduce our wonderful speaker tonight, Leonard Susskind. I've known Lenny for more years than I care to think, probably, and likewise, no doubt. And, I'll respond to that in a moment. We tried very hard to bring provocative, challenging thinkers that are kind of, pushing the frontiers and working on the edge. And there are very few thinkers in today's world more on the edge, in more ways than one probably, than our speaker tonight. Lenny is a distinguished theoretical physicist who has made innumerable fundamental contributions to the field of fundamental physics, may be identified as a high-energy physicist or an elementary particle physicist or just a fundamental physicist, a physicist working on fundamental issues in physics, conceptual issues, and tonight's subject is obviously quintessentially one of those. And Lenny is maybe best known of all the many things that he has done sort of in the public eye for, on the one hand, being one of the inventors, so to speak, of string theory, the idea that the fundamental forces, the fundamental objects, so to speak, of nature are not little Newtonian-like point particles, but are more little vibrating strings, and everything around us comes from the geometry and dynamics of the vibrational modes of those strings and the way they interact and so forth. He was one of the founders of that whole idea and has been instrumental in developing it. But also he's known for a dispute that he had with Stephen Hawking about the role of information and black holes, that the idea that black holes swallow everything up, including all information. This was a major dispute which lasted for, 20 years probably, and which Lenny eventually was declared the winner. And this is no mean achievement, and indeed Lenny wrote a popular book on the subject, for which I think you got a prize for that one, actually, a book prize for that. So he's not only delved into the depths and fundamentals of physics, but he's also been a popular writer and written best-selling science books into the bargain. So, as I said, I've known Lenny for a very long time, for probably 40 years, and one of our disputes, mini disputes, is to do with time. Because every time we meet, Lenny thinks that I'm older than he. He knows in the beginning, he knows that when we first met, that I was younger than he. And so he has, as you will see tonight, a very interesting ideas about the concepts of time that somehow... So we had breakfast a week or so ago with our two delightful, beautiful wives with us in Palo Alto, and it came up again. But I did discover that a week or so ago was Lenny's birthday. So many happy returns, and I'd like to... And Lenny is now 73. I, of course, am only 72. So, having said that, I've known Lenny a long time, and I think you're in for a good show tonight, and certainly something that is going to be very mind-challenging, and as well as, no doubt, entertaining. As I say, we've known each other. We have done some adolescent things together. We were thrown out of a bar together in, I guess it was Miami, but it might have been Coral Gables. Anyway, there was a famous meeting in Coral Gables every year on some of these fundamental areas, and we went to it. And he reminded me in 1975 is the time we were thrown out of a bar. It may have been the same year that he undressed at a dinner party around a pool, and everybody thought he was going to be in his underwear, but he was actually in his. He often claims that I did the same thing, but I'm British, whereas he's from the South Bronx. And I'm going to finish up with something he told me today that I didn't know about him, is that his name isn't Leonard. Lenny's first job, so to speak, was as a plumber. He was trained as a plumber by his father. And his father had great admiration for Leonardo as an engineer and named his son Leonardo. So he has an unusual name, may I say, for a Jewish boy from the South Bronx. Leonard Susskind. But Lenny went to City College as an undergraduate and was a graduate student of Cornell under a man named Peter Carruthers, who also influenced me at some stage in my career, and then was taught at Yeshiva University in New York for several years before moving, I guess it must have been late 70s, maybe around 1980, I don't remember exactly, to Stanford, and has had a glorious career and been one of the main beacons in terms of fundamental questions, one of which will be you will be exposed to tonight, and that is the nature of time. So with that, let's welcome Lenny. You can walk around. Or up there, go at the middle.
Frankly, I really prefer to stand right over here.
Yeah.
But, okay, I can't. They won't let me. Kurt Vonnegut once started a lecture. I think he was addressing some librarians. I'm supposed to stand over here. And he said, I'm 52 years old, I'm a grandfather, and I can get to do any damn thing I please. And a piano rolled out, and he started to play Stardust. He said, I always wanted to play Stardust. Well, I'm not 33, I'm 73. I'm a grandfather 9 times over. I have 3 great-grandchildren, and by damn, I can do any goddamn thing I please. What I feel like doing is what my grandmother called kvetching. Kvetching means complaining, and I'm going to complain right now. It's not a very gracious thing to do when you're invited to give a lecture, but I'm going to complain about the venue for the lecture. My complaint is that these goddamn machines are ruining my culture. In the old days, when you went to a lecture like this, a physicist would get up and with nothing but a piece of chalk in his hand to defend himself and to attack you and do whatever it was he was going to do, that professor would get up and there was body language. There were gestures. If he was any good, there was a ballet. Sometimes they were bad. There was one fellow, well, you know of course who was the great master of this, was Dick Feynman, an old friend of mine. There were some people who were bad at it. There was one guy, very, very famous, incidentally, I won't mention his name, and he would stand at the blackboard and make little tiny things, and he would mug, and then he would turn around and look at the audience. He was terrible, but it was a human thing. You very well remembered who the lecturer was. And you remembered what he did, and you remembered how he moved. These days, it's completely different. You stand at a computer like this, and all you get to do is push buttons. This, to me, is the ultimate degradation of my culture. And I am going to say the next time I come back here, I want a blackboard. Okay, I'm going to do what every old physicist does just before he becomes senile, or just after he becomes senile, I'm not sure which, I'm going to talk about time. Everybody talks about time when they get to be a certain age. They think maybe they understand it or they don't understand it, but they have this inner need somehow to express themselves about time. I didn't think much about it, but it might be because they don't have much time left, I'm not sure. But what we're going to talk about today, my transparency is perfectly clear. It's perfectly clear what it says up there. It says future. Past to future. This is not my fault that it's off the slide, and it's probably going to be more off the slide as far as I can tell. In any case, why is the past different than the future? Now, the past certainly is different than the future. Let's see if this thing will work. Yeah. If I show you the slide, no doubt you will say, that's the past, and you'll be right. That's Los Angeles, circa, anybody want to guess? I would guess 1939. You think it's 34? The cars look to me like 39, but I'm not sure. I'm not sure. So anyway, no doubt, there's nobody here who thinks that's the future, right? Nobody thinks it's the future. And if I showed you this, well, you'd probably say, oh, that's a picture of the future. But there's a big difference. The big difference is we know the first picture was the past. We have no idea if this is going to be the future. It's a wild speculation. It's not going to be very likely that that will be the future. And so we can ask the question, why is it so much easier to know what the past was than what the future is? What is this asymmetry between time in the future and time in the past? Now, no doubt, the ancients probably before, maybe before the 19th century, would have said, that's a stupid question. Of course the past is different than the future. We don't have to explain that. It's just manifestly obvious. Things that have happened have happened. Things that haven't happened yet haven't happened. But as physics became more mature, it became very clear that this was, yes, sometimes, incidentally, sometimes I blow it on the transparencies and I get ahead of myself, so I just did. But let me come back. The archetypical example of the one-way street of time is the second law of thermodynamics. It's a law of physics, and it says that entropy always increases. Now, you don't have to know for this talk what entropy is with any precision. You just have to know that there's this thing called entropy. It has to do with confusion and chaos and so forth, and it always increases. Entropy always increases as a basic law of physics. But where does it come from? The laws of thermodynamics originate out of the laws of particles, out of the laws of Newtonian mechanics, out of the physics of more elementary things. Are the laws of nature, the very, very basic laws of nature, the microscopic laws of nature, Newton's laws, are they asymmetric like that? Do they distinguish the past from the future? And the answer is no. If you have a situation in which you you see, I got ahead of myself again. I do this over and over again. Yeah. Let's go back a step. Let's go back to Einstein. Einstein wasn't so much concerned with the second law of thermodynamics, but he was very much concerned with space and time. The only thing for this purpose today about space and time that I want to remind you of is that Einstein said that space and time together make up a common object called space-time, and that time and space are deeply interrelated in such a way that space and time, x, y, and if I had an extra axis on here, I would draw z, x, y, z, and t form a common thing, and that time is really no different than space. Well, nobody thinks that x to the right is different than x to the left. The laws of physics are certainly symmetric with moving to the right or moving to the left. They're the same for moving out of the blackboard and into the blackboard. So what is it, if Einstein was right and space and time are really of the same nature, how is it that time seems to be so asymmetric to us? Why is time a one-way street when certainly X and Y are not one-way streets? So let's look for an answer, see what we can find out about it. Let's go back to the very, very basic principles of Newtonian mechanics. Here's a picture of the solar system, and Newton himself would have told you that you cannot tell from this picture whether the planets are going to move clockwise or counterclockwise. If I told you the planets always move clockwise, you would probably say to me, there's no reason why planets always move clockwise. If clockwise is a possible orbit for a planet, counterclockwise is also a possible motion of planets. So the fundamental laws of physics, in particular Newton's laws, are not asymmetric with respect to time. Anything that can happen, the opposite can happen. Any movie picture that you were to make of this, you could run it backward and you could not tell the difference. So the fundamental laws of mechanics, Newton's laws, do not distinguish the past from the future. Likewise, the laws of quantum mechanics. The fundamental laws of quantum mechanics, the fundamental laws of atoms, the same thing is true. You cannot take a picture of an atom and tell whether it's going backward or forward. The laws of physics are completely symmetric. So what's going on? Why is it that the world looks so asymmetric? As far as I know, the first person who asked this in modern form was a great hero of mine, Ludwig Boltzmann, who was very worried about the second law of thermodynamics. He could not understand why it should be so that if the laws of physics, the basic laws of physics, are the same forward and backward, how could it be that entropy always increases? He thought about it, and he thought about it, and he thought about it, and in his profound wisdom, he came up and said, entropy almost always increases. That was Boltzmann's great contribution to physics. Oh, this was a very big one. This was a very big and deep insight. It was not his only contribution to physics, but in many ways, I think this may have been his greatest contribution to physics. To understand that the second law of thermodynamics is not exactly a law in the same way as conservation of energy, in the same way as F equals ma. It's not always true. It's just almost always true. It's a statistical law. It's a probabilistic law. Doesn't mean you can't see something crazy happen that you wouldn't expect going backward. It just means most of the time you don't. Now, we can discuss how many times you're likely to see something crazy. What do I mean by something crazy going backward? You spill your bowl of oatmeal on the floor and goes plop onto the floor. Very rarely does the oatmeal assemble itself, jump back up into your bowl. The laws of physics permit it. Now, in order to have it happen, you would have to have all of the molecules both not only in the oatmeal, but also in the floor and all around the atmosphere and everything else reverse themselves very precisely. But if that were to happen, the laws of physics would tell us that that oatmeal would jump back into the bowl. Does it happen? Well, given enough time, it will happen. But it hardly ever happens. As I said, that was Boltzmann's great insight, or one of his great insights into physics. Boltzmann went further. He wanted to understand deeply, more deeply, why the universe is a one-way street, why entropy always increases. He was not a cosmologist. At that time, there was not the subject of cosmology. But from what I understand, from what I can glean from historians, from people who have studied what Boltzmann did, Boltzmann had a very modern idea of how to think about this. I'm going to put words in his mouth. I'm going to put words in his mouth, but I think they are words that he might have said. Boltzmann was interested in the universe. He was interested in why the universe proceeded in one direction. And one model of the universe that he made, he really did, this exists in the literature, was the universe in a box. a closed, sealed box, like this room except without doors, without windows, full of whatever it is it's full of. That was a model for the universe that Boltzmann was interested in. Now, let's start here. Let's take away the letters and start with a completely empty universe. A completely empty universe, nothing happens. It doesn't go forward, it doesn't go backward, it just sits there. So it's completely symmetric. What Boltzmann said is, let's start a universe in a very, very unusual situation. One that is very, very special. It didn't much matter what the special situation is, but it should be special. Here was a special situation that he imagined. A large number of molecules, 10 to the 80th of them, that's about the number of protons in the visible universe, start with a large number of molecules or atoms or whatever it is, all in the corner of the room, all in the corner of the box. The black rectangle here is the boundaries of the box, and Boltzmann said, put all the particles into the corner. Start it that way. What will happen next? Well, you can guess what will happen next. If you're a little bit perverse, you might say, oh, they're going to squeeze themselves even tighter into the corner of the room. Doesn't sound right. Much more likely, although they could do that, it could happen, but much more likely, most of the times if you found molecules like this, you would find them streaming away from that point. You would find them streaming away from that point, and here's something that Boltzmann imagined. I imagine Boltzmann imagined it. Boltzmann imagined that the molecules would swarm away, and in the process of swarming away, during the time that they were flowing away from the corner, in the process of flow, some turbulence might happen. The turbulence might create little eddy currents, little swirls, tornadoes, hurricanes, whatever, and these swirls might have structure in them. It's not by accident that these look like galaxies. I meant them to look like galaxies. Again, I get ahead of myself, but okay, let's go there. He said, during the process of moving away from this very special state, things can happen, structures can form, eddy currents can form, and during that period is when everything interesting in the universe must have happened. Ultimately, if you wait long enough, everything evaporates, everything turns into evaporation products, photons and elementary particles. Nothing is left but particles in thermal equilibrium. Particles in thermal equilibrium means particles uniformly filling the box, randomly moving around, and that's it. That's the end game, just what a physicist would call thermal equilibrium. Boring, it lasts forever, and nothing else happens. So there's a short period in Boltzmann's box during which some interesting things happened, and then nothing. Just heat death. Heat death, called heat death, or entropy death. Entropy death, everything fades into a meaningless, boring uniformity. But Boltzmann knew this wasn't quite right. He knew this wasn't quite right, and what he said is, if you wait long enough, just by accident, by the laws of large numbers, just by statistical probabilities, if you wait long enough, I won't tell you how long it is, far, far longer than the age of our universe, but if you wait long enough, by accident, the molecules will just accidentally reassemble themselves in the corner of the room. And the whole thing will happen over again. So the end game was not really the end game. It's just the end game for a long, long time. These are called recurrences. They're called Poincaré recurrences, but I think the idea was first due to Boltzmann. Things will recur if you wait long enough. Now, Boltzmann formalized this idea in the following way. He said, let's take the space. Physicists and mathematicians are always putting everything in a space, not our space, but in a space. Let's take the space of all possible configurations. Why does this happen? I'm going to go back. Yeah. All right, the space of all possible configurations, This region here, the black, inside the black region, that's not the universe. It's all possibilities for where all the molecules could be. Now, up in the center there, you see a little pink dot. I will not try to aim this thing at it because it will just flip the transparency. There's a little pink dot in the center of the blue region. Think of the little pink dot as the very special starting point. It could be the place where all of the molecules are in the corner of the room. The blue region is all the possible regions where there's interesting structures, galaxies, planets, all those sorts of things. And the white region is just the boring equilibrium, the dull, boring equilibrium where nothing happens. And Boltzmann said, look, if you start, if for some reason, unknown reason, we don't know who put the molecules in the corner of the room, but if you start there and you let the system run, it will move out of that region into the blue region. That's the molecules forming clusters, forming eddies, forming galaxies, forming whatever it is they form, people. But if you wait even longer, and that's good, that's a good theory, that's a nice theory. It tells you that with a starting point which is special, you can get where you want to go. Where you want to go is where Boltzmann found himself in a world full of structure. But he also realized something else. He realized if you keep going and wait and wait and wait, the universe will pass through every possible state. Many times, just statistically, it will wander around in this space over and over and over again, every now and then passing through the blue region. Sometimes, most of the times, it will pass into the blue region without going through the pink region. The pink region is a little tiny dot with almost no probability at all. The blue region is bigger. Technically, we would say it has more entropy. The white region is the biggest of all. It's the most probable. And the universe wanders around in the space of possibilities, every now and then passing into the blue region. When it's in the blue region, people can exist, planets can exist, and so forth. But when it does so, most of the times it doesn't pass through the pink region. That means most of the times, almost all the times, if you find yourself in a world more or less similar to ours, the past history does not look like what you might have expected, namely all the molecules coming out of the corner of the room. In fact, you might find yourself in a universe, this is a universe born out of fluctuation, a universe born out of random fluctuation, just by accident, a universe formed. This is something deep that Boltzmann realized, but he also realized that most of the times that universe is not going to look like what you would have expected in a theory, in an ordinary theory where the molecules float out of the corner of the room. Flowing out of the corner of the room is just a substitute for the Big Bang. The Big Bang, the universe started small, it started concentrated, it started very special, and it leaked out. Think of it that way. What Boltzmann understood is that most universes that are created out of fluctuation don't look recognizable. They have properties that don't make sense. They might look like this just as likely as they would look like a bunch of galaxies. So Boltzmann understood that. He rejected this as a possible explanation of the world. He understood that the world was not a world in a box, but he didn't know what else to do. He didn't know how to think about it. He didn't know how to understand the fact that the universe in our past does look special. You see, the problem here was only the first time, if the universe drops out of the corner of the room, only the first time does it look like something we recognize, galaxies, so forth. Most of the times, endlessly, it looks like random garbage. Random garbage, but good enough for us to live in. So you ought to predict in a universe like that, not that there was a Big Bang, not that the cosmologists who study cosmology got it right, but you should predict a random past which doesn't look anything recognizable. Now that's crazy. Boltzmann, as I said, knew it was crazy. In fact, he understood, but a modern version of it is if you ask the question, what is the most likely thing, the most likely configuration that would form out of chaos in this way, by fluctuation, by randomness, what's the most likely thing given that it has to be, that it has to have intelligence so that it can ask about the world? Well, the answer is the most likely thing to form would be one brain and nothing else. One brain and nothing else, because to make two brains is much less probable than to make one brain out of chaos. The most likely world that would contain an intelligent creature that could ask questions would contain one brain. Physicists these days call it a Boltzmann brain. This is called a Boltzmann brain, and of course, this is not the right theory of the world. We don't live in a world where there's only one brain, so this theory is not the right theory. It's clearly wrong. But what's wrong with it? Okay, so now the question is, what does modern cosmology have to say about it? Wouldn't it be better to have a one-shot world? A one-shot world means the molecules come out of the corner of the room, they do their thing, and then they go off and we never hear about them again. No possibility of these recurrences going on and on and on and telling us that the most likely thing in the world would be a single Boltzmann brain. A one-shot world is a kind of goal of cosmology. By one shot, I mean the whole thing happens once and it doesn't recur, and it's not a universe in a box. It doesn't come to equilibrium. The molecules flow out once, produce tornadoes and whatever it is they produce, and then go off and they're gone. That, you would still have a problem. You would still have to explain why they started in this very special configuration. But maybe someday we'll understand why they started in the very special place. Okay, so is that consistent with modern cosmology? Let me talk a little bit very, very quickly about both yesterday's cosmology, and by yesterday's I mean 25 years ago, versus today's cosmology. And we'll see what we've learned. 25 years ago, there were two cosmologies, two versions of cosmology, one of which nobody knew which was right, but it was believed that one of them was right. They were called Big Bang cosmologies, and there were two versions, open and closed. An open cosmology, the universe was infinite, but more than that, it continued to be infinite and continued to expand. A closed cosmology had the property that it expanded and contracted and crunched, ended in a big crunch. Now this picture here, this is a graph. On the vertical axis is the radius of the universe at any given time, and on the time axis is the time. The left-hand side, the left-hand corner is the starting point, the special starting point. The universe starts very small. It begins to expand. Interesting things happen during the expansion. Interesting things mean, I'm putting this down. Interesting things mean all the good things that we're looking for. And then it comes back and dives and crashes, crunches. The universe just crunches to a point, and it's over. That's clearly a one-shot universe. You get one chance. That's the end. It's fine, except you have to explain why you started in the special state. The other version, which is also fine, is called the open universe, and it's a universe which just continues to expand, so the radius of the universe just expands and expands and expands. Now, because it expands, all the particles fly apart. If they fly apart, it's still true that you only get one shot. They fly apart. Once they're flown apart too far, they cannot interact with each other anymore. They don't form galaxies. They're finished. They may still be there, but they're flying apart from each other, and they're not useful for making even a Boltzmann brain. So again, an open universe is also a one-shot universe. And so this is good. We have an explanation of the world. One-shot universe, except that we have to understand the starting point. All of this was understood. It was thought to be the solution of the problem until about 15 years ago, 10 years ago, and so forth. Dark energy was discovered. To a physicist, dark energy is called lambda. It's called the cosmological constant. It doesn't matter whether you call it the cosmological constant or you call it dark energy. It's a condition in space whose effect for our purposes is one of two effects. Either it accelerates the expansion and makes it even faster than it would be without the cosmological constant. In fact, it creates accelerated expansion, which keeps accelerating and accelerating and accelerating. That's if lambda is positive. If lambda is negative, it does exactly the opposite. It accelerates the crunch. It kills the universe even faster. Think of the crunch as being the universe being killed and ended. The other possibility, lambda positive, is the universe acceleratedly expanding. Now, either one of these, there's a picture for lambda positive, incidentally. This is to be compared with the open universe, which I described before, where the curve just went off into the upper right-hand corner without curving upward like that. Positive lambda, positive cosmological constant, positive dark energy makes the universe expand even faster at an exponential rate, an exponential growth of the universe. That actually sounds very good for one-shot universes. The other possibility, as I said, is the negative lambda, and that causes the universe to crash even faster than it would have if in the closed universe. So it's sudden death for the universe. Both of those sound, as I said, like reasonable candidates for one-shot universes. Everything interesting starts in the beginning of that curve, and then the universe is finished with its thing. Well, in our universe, lambda is positive. It's exponentially expanding. That's an observed fact. That's not a conjecture. It's not a theory. It's an observed fact. Our universe is expanding at an exponential rate. And this sounds great for one-shot theories, but it's not. So let me explain what's wrong with thinking of the accelerated universe as a one-shot universe. This is a picture of Hubble's law. Most of you know, probably most of you know, first of all, I'm sure most of you know the universe is expanding, and you know it's expanding according to Hubble's law, which says that the velocity of recession, away, the center is the sun. The galaxies are moving away from us. The further away they are, the faster they move. That was Hubble's discovery, Edwin Hubble. He discovered that the velocity of recession is proportional with a constant called Hubble's constant times the distance. The further away you are, the faster you're moving. And there's a constant of proportionality between them. Now, this constant is not really a constant in most cosmologies. It decreases with time. But in an accelerated universe, the kind with a cosmological constant, the kind that we know that we live in, that Hubble constant really is a constant. Now, that in turn means that if you go far enough away, there is a place where things are receding away from us with the speed of light. How can we find out how far? We just substitute for v, the speed of light, and solve the equation, and that equation tells us how far away we have to go until we come to the place where things are receding away from us with the speed of light. If they're receding away from us with the speed of light, then anything that's further away from that cannot be seen. The recession overwhelms the velocity of light and prevents even a light ray which is trying to get back into that circle. It's swept away with the expansion, so nothing outside that region can ever be seen in an accelerated universe. The circle where that happens is called the cosmic horizon. It is very much like a black hole horizon, except a black hole inside out. You don't lose things into the black hole, in this case. You lose things to the outside because they pass out of the cosmic horizon. So, the accelerated universe has a horizon, no big deal. Here's a picture of the accelerated universe. Everything out behind the horizon we can never see, so I've painted it black. Cannot be seen. Inside, there's our galaxy, there's the Andromeda, there's all the distant galaxies, And there we are, but they're moving away from us. They're rushing away, and they're rushing away so fast that when they get to the edge, they're moving with the speed of light, and then faster than the speed of light, and we cannot see them. That's the picture of the accelerated universe, the classical standard picture. It's called de Sitter space, and that's what it looks like. Now, if you wait a while, all those other galaxies will pass out through the horizon, and we won't see them. That's probably in our future, not our personal futures, but the future of our galaxy. In time, about 1 trillion years from now, or maybe it's 100 billion, I don't remember, a few 100 billion years from now, all of the galaxies, or most of them, will have moved out through the horizon, and we will truly be alone. There will be nothing in our astronomical sky other than just plain emptiness, or almost emptiness. Still sounds pretty good for one shot. But if you even wait longer, the galaxy itself will evaporate. The protons that make up the galaxy will probably disintegrate. They will form radiation. The radiation will pass out through the horizon, and there will be nothing left. That's the standard picture of the accelerated universe. And I'm going to emphasize once more, that sounds awfully good for a one-shot universe. It only happens once and then it's gone. But quantum theorists know better. They know, and this is largely the work of Hawking it's largely the work of Hawking. Hawking understood that the horizon of a black hole, or the horizon of the cosmic horizon of the universe, is not a cold, dead place. It has quantum energy, and that quantum energy gives it a temperature. It behaves as though there actually were particles in a box. Now, most of those particles are concentrated near the boundaries of the box, near the cosmic horizon, but they're constantly fluctuating. They're constantly in thermal motion. And guess what? Every so often, Boltzmann rears his head and says, every so often, those particles will assemble themselves into a structure of some sort. If you wait long enough, of course, what will happen to this Boltzmann brain? It too will evaporate and disintegrate, but wait a little longer. Not a little longer, a lot longer, and another one will appear, and then another one. So we haven't escaped from the conclusion that in this kind of universe, almost everything that ever forms, overwhelmingly probable that if you find an intelligent object, that intelligent object will be something very, very different than us. This, believe it or not, cosmologists and physicists worry about this. They worry about it not because they're worried that we are Boltzmann brains, we're not. But when you have a theory which gives predictions which are absurd, you can ask yourself the question, is your theory right? Your theory is probably wrong. There's something wrong with a theory that says that the universe simply forms a box with thermal particles in it. And unfortunately, that's exactly where modern cosmology has led us. By virtue of the dark energy which makes the universe expand in an accelerated way, it has led us literally right back to Boltzmann's box. It has led us right back to Boltzmann's box. Something is wrong with our cosmology. Okay. I could leave it there. I could say that's the great puzzle of time in our time. We've gone through some cycles, and that's where it's left. But I won't. I will try to take you a little further and tell you a little more. You know, I was going to use the blackboard, but, you know, I am 73 years old, and I'm getting tired. So I'm going to use the machine. As much as I hate to use the machine, I'm going to use it. I'm sorry, Jeffrey, that I made you bring this thing here. I know you carried it on your back yourself. I know Jeffrey carried it. He walked from the Institute. It couldn't fit in his car. He carried it on his back. And I'm sorry. And I said, Jeffrey, you have to do this for me. And Jeffrey said, well, yes, all right. If you promise not to tell what happened in Miami Beach in 1975, I will carry it here. And I promised. but I can't do it. I'm too tired. So I'm going to go on with the slideshow. All right. The next step in cosmology, and one which is speculative, honestly speculative, we do not know if it's correct. Some of us suspect it's correct. Some people are very derisive about it and say it's silly, it can't be confirmed. I'm not going to try to convince you that it's correct, but it may be a component in solving this funny problem about Boltzmann's problem about time. So I will tell you what it is. The multiverse theory begins with a space-time, that's space, and it's empty space. It's completely empty space, but it's rapidly expanding space. It's space with a cosmological constant. It's space with a lot of dark energy. And although, because it's empty, you can't see what it's doing, but it's expanding like a bat out of hell. It's growing very rapidly. And in an expanding universe, expanding that fast, fluctuations happen. Things do happen even though it's completely empty. One of the things that can happen, which was discovered in the 1970s by Sidney Coleman and his collaborators. Sidney Coleman was one of the great physicists of our generation, of my generation, and my younger friend's generation over there. Sidney Coleman discovered that a universe like this, from time to time, will boil a bubble. Just like boiling water will create a little bubble. Now, it's an unlikely thing to happen, but that just means it takes a long time. And when it happens, a bubble forms. In that bubble, the properties of space and time are a little bit different, or maybe a lot different, than in the blue region. Space and time and physics and particles, the constants of nature, are different in the red region and the blue region. The red region starts to grow. And it grows, and it becomes in itself, in its own right, a growing universe. We could live in there, maybe. Maybe we could live in there. But in that universe, another little bubble can form. And this goes on and on and on. It's a free lunch. There's nothing to prevent this thing from going on and on and on forever. That's the mathematics of it. The mathematics of it keep boiling off, and when I say the mathematics of it, I mean the quantum mathematics of it. Keep boiling off bubbles, 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 bubbles. Each one of them could be a little universe in which we could live, and each one is different from the other. I'm going to show you a way of thinking about it, and then I'm going to tell you a little bit about the mathematics of it. I see we still have about 15 minutes, is that right? Yeah, okay. All right, so this is what I was going to draw on the blackboard. All right. What is it? The starting point down at the bottom is a growing universe, but it hasn't grown very much yet. Can you see the colors? Are there colors on there? From where I'm standing, there's no color at all. The colors are fine. Okay. What's the color down at the bottom? Red? It should have been blue because it should have matched my previous color. That's the starting universe. It's starting to expand. Every time it expands, it doubles. Let's say over a certain period of time, it doubles. Whenever it doubles, I'll represent that by the universe growing into two pieces, but then because those pieces separate from each other, because they're growing, they separate from each other, they get too far from each other to communicate, and so I'll just represent that by the universe bifurcating. Now, it doesn't really bifurcate. This is what you would call an idealization or simplification. The universe doubles, and then it doubles again, and it doubles again. What is the color coding? The color coding is exactly the colors of the bubbles that we started with in the previous slide. Different properties. Each one of these lines is a universe in which somebody could live. Maybe they could live. Maybe the properties are appropriate to live in. And it just keeps going on and on, growing and growing and growing. As it grows, it produces more little pockets, It's diverse. Different pieces are different than other pieces. And there's a probability distribution of some kind telling you how probable it is as you move up that you're in a red universe or a blue universe or a green universe. these different colors could just stand for whatever different properties you like, whatever they happen to stand for. Different properties, and notice that there are places where the colors change. Those are these Coleman-DeLucia processes which boil off bubbles of a different type. That's kind of what, that's not kind of, that is very much like what an inflating universe looks like if we take into account that these bubbles can happen, that the Coleman-DeLucia bubbles can happen. Looks pretty much like that. That's a fairly good guide to it. All right. Let's imagine, oh, here is where I was going to write some equations. Let me write the equations. Okay. You could ask the question, what's the number? What's the mean number, the average number of lines, bubbles, universes, whatever you want to call them, of a given color at a given time as you move up? Time moving up comes in discrete steps, the bottom, the next layer, the next layer, and the next layer. And you could ask, tell me if you can't see this and I'll make it bigger. What is the average number? Can that be seen? Yes? Good. What's the average number of universes or bubbles of type M? M could stand for red, blue, green, whatever it stands for. At time t plus 1, what's the average number at time t plus 1? In other words, when you go up a level of bubbles of type M, and that is equal to the average number of bubbles at time t twice the average number at time t. Why twice? Because it doubles at every stage. At every stage it doubles, so there's a source of new things. The source of new things is this doubling. That's the first term. Now, you lose some lines of type M. A blue line can turn into a red line. So you lose some, so you have to subtract. And what you have to subtract is a certain number, which is called gamma, and it's the probability that a universe of type M will spit off a bubble of type N times the probability or times the number of things of type M. This is summed over N. Don't worry if you don't know. I'll explain what this is, but I just for the experts in the audience, and there are experts in the audience on these kind of equations, I'm going to write the equations, and then I'm going to tell you what they mean. All right? And then there's another term which increases. This is loss. Things of type M become things of type N. So you lose things of type M. Right? But you also gain things of type M if N becomes M. And that's N sub N. Also summed over N. That's an equation. It's got a name. It's called a Markov process. I wanted to show you a picture of Markov, who was a very, very famous Russian mathematician and was responsible for these kind of equations. I looked on the internet and I finally found a picture of Andrei Markov, and it turned out to be a Russian not a soccer player. You know, those guys who beat each other up with sticks. Hockey player, yeah. Right. I'll just tell you briefly. What this equation says is the number of each type at a given level is, first of all, the number that were there before that but doubled because each time it doubles, plus some loss because you lose some of that type when they become other types, plus a gain when other types become the type you're interested in. So it's a balance. It's a balance, a statistical balance. Anybody who knows this kind of equation knows how to solve it. And guess what you find when you solve it? You find that if you were to follow one of these tracks, branches, you are somebody who lives in this. You don't get to see the whole thing. All you get to do is follow along a line, a branch, leading to a branch and a branch, and these equations simply tell you what the probability is that you see different things as you move along the branches. Guess what it says? It gives exactly the same answer as Boltzmann's box. Exactly the same kind of answers, the wrong kind of answers, the kind of answers which say you come to a dead end of equilibriums and fluctuations, and in this kind of universe, you lose again. You're back in Boltzmann's box. Even though it doesn't look anything like a simple static box. It doesn't look anything like it, and yet it comes back to exactly the same thing, the simple static box, if you follow your way along there, and what you find is a universe dominated by fluctuation, where almost all of the time, if you saw something, it would not look like what you would expect to see because it grew out of fluctuation rather than the one-shot kind of... In other words, the point is, you keep going up and up. That doesn't terminate like that. It goes up and up and up and up and up and up. And if you keep following it up, you eventually just discover that there are recurrences, back and forth, Boltzmann's brains, normal universes, and you haven't won. You still have not understood why time is a one-way street that goes from something very simple to something complex, and that's it, end of story. You have not explained that. Well, I like to describe this by saying that it's led to a stagnant pool. It's led to a stagnant pool in which the only things that ever happen by random fluctuations. If a little vortex happens, it happens not because there's a flow of water, but because just by random accident some molecules might assemble themselves into a vortex. That vortex is very unlikely to look like the kind of vortex that you would get from a flow of water. The universe expanding out of the corner of the room is like a flow. This is like a dead end. So almost every theory we know of the universe either is empirically wrong or ends in this kind of dead end where the things that happen are just random fluctuations. However, remember I told you about the crunches. If there are cosmological constants which are negative, the universe can crunch. Well, that means these bubbles have the potential possibility of dying. This is very much like the tree of life, and the dead ends are like species which just die out to some extent. Red might correspond to the kind of universe that crunches. It ends. If it ends, it doesn't continue to branch, it doesn't continue to grow. You have to modify the equations. The modification of the equations involves one new term here. The one new term has to do with the probability of dying. And that just gives you a minus. Why? A minus because it removes probability. A constant, doesn't matter what it's called, gamma m times nm. Now don't worry about the equation. The main point is it changes the equation. And what does it change the equation to? Let me just look at these terms. This term is a kind of source. It's creating new things. This is a sink. It's eating up things. The equation has turned into an equation which is very, very similar to the equation which you would have if you had a source of fluid on one end and a sink down at the other end, so that the fluid flowed from left to right, from source to sink. Well, guess what happens when a fluid flows from source to sink? It creates eddies endlessly. It creates vortices endlessly. Those vortices, however, have a very definite sense of time. Time does run from left to right. Somebody living in one of those vortices would realize the vortex was born somewheres and would run out of steam somewheres. Very unlikely to see a vortex propagating in the opposite direction. A flow like this is exactly what you need to understand why time is a one-way street. The multiverse, the idea of a fractal flow, these equations here, appear to be possible to give you a universe which runs in one way. Now, is this going to run into trouble? Are people going to analyze it and discover again that it leads you back into Boltzmann's box? I don't know. But at the moment, this is the state of the art. This is as much as we know. I've taken you through all the various cosmological assumptions from Boltzmann's box to the fractal flow and told you what they have to say about the arrow of time. I don't think we're finished. This may or may not be the right answer. And if you invite me back with a blackboard in about 5 years from now, when I will be 78, I will try to tell you the answer. Thank you. Well, the only problem is I don't have my glasses.
So thank you, Lenny, for a wonderful talk. Very stimulating and very provocative, very challenging. So we have time for a few questions. I think I'll let, since he's up there.
Well, the problem is I can't see it. I don't have my glasses.
Oh, okay, I'll see. Well, I can't see either, actually. So let's see. I saw a lady over here, yes. And speak up, stand up.
Yeah.
And speak up.
It's important that you speak loud because both Jeffrey and I are both deaf.
We're both deaf and we can't see. I don't have an explanation for that, but I think I could concoct an explanation why some brains think they can do that and others cannot. But I will not, I am not going to tell you that I know that people cannot do that. I once watched a man do a very amazing thing. He, do we have an extra 2 minutes? I saw him do ESP tricks. The ESP tricks were absolutely remarkable. Somebody got behind him, and by pure process of thought, I was the one behind him, in fact. By pure process of thought, I guided him forward and told him what to do. The guiding was go forward, go forward, go forward, go forward, go left, go left, go left, go left. Raise your arm, take the chalk, and write a vertical line on the blackboard. And he did it. And he did it 9 times out of 10. And I was the only one in the audience who knew what he was supposed to do. I said to him afterwards, Shmuel, his name was Shmuel Gurvitz, he was a physicist, right? He did this. I said to him afterwards, Shmuel, this is crazy. Do you have any idea what you do? He said, no, I don't know what I do, but I'd be willing to try to find out. So we did some experiments. And we did this over and over again until I began to realize that he was picking up on the tiniest little body gestures of mine. As we went forward, I would go left, go left, go left. And his eyes were going back and forth, and he was picking up on this. He was hypersensitive in a crazy kind of way. I asked him, Shmuel, where the hell did you learn how to do this? And he said, well, it was in the Russian army. The Russian army was trying to detect submarines in the Baltic. And so they got a whole bunch of extremely sensitive people who showed an extraordinary ability to do this, and they started training them to try to detect submarines in the Baltic. They didn't detect submarines in the Baltic, but the moral of the story is that some people are extremely sensitive to certain small signals and so forth. So it wouldn't surprise me if there are people who can pick up on things that most of us can't. That's all I'll say. Ghosts know, but... Let's see. Let's do this gentleman in the back. Speak up when you ask. It does allow bubbles to collide with each other.
And if bubbles collided, if a bubble collided with our bubble, assuming we live in a bubble, it could conceivably be an observable event. It could have an observable imprint on the microwave background on the sky. At the moment, people have looked for it. This was a reasonably high priority thing that cosmologists searched for, observational cosmologists, and they did not find it. However, theoretically, it's a highly improbable thing. So, but they can collide with each other.
Let's do this gentleman here. Oh, yes.
In the law about constant receding
Hubble's law. Hubble's law.
yeah, how could we be at the center of that?
We're not at the center. Everybody sees the same thing. But for that, I suggest you take my online cosmology course. No, it's good. It's good. It answers all questions like this. And it's called the Theoretical Minimum. They're online cosmology courses. And the books will come out, and the books will be cheap, and you can buy them and they go along with the course. But the answer is nobody sees anything different than everybody else. Everybody's separating from everybody else. But you have to draw the picture, and the only way to draw the picture is to pick a center and say somebody's at the center.
Just from over here, this gentleman here.
That's the question. Are you or aren't you? And I have to say, personally, I'm confused by it. And I think everybody who does this is a little bit confused. Okay, yes, you're picking a time, you're picking the direction that you're calling up. You could turn the whole thing over and call the big growing tree the past, but it would just be a word. You would just be calling it the past. Something, the diagram is breaking the symmetry, is what physicists would say. And I think you might say it's either one or the other. Both can happen, but they would be essentially identical, and you couldn't, people who lived on it couldn't tell the difference. But I think you've asked a key question. Have you, by drawing the picture the way I drew it, prejudiced it so that there's already an arrow of time? And that's a good question, to which I won't try to answer. I think the answer may be no. We may be lucky, but it's unclear.
That's over here, over in the corner.
Oh, it might have different constants of physics. The fine structure constant might be twice as big, or the cosmological constant might be 10 to the 100 times bigger, or might have different particle content. The proton might be heavier than the neutron.
Could you imagine the form of the equations being different, the principles being different?
Well, you could imagine the form of the equations that we use today being different. But you could ask, would there be underlying equations which could govern the whole thing, and for which these were different solutions? Yes, very much so, and that's what's one of the things we learned from string theory, is that string theory does have the capacity to describe many, many different things. So, whether the equations that we use are sort of a temporary thing that depends on the age at which we're using them. Yes, you can imagine that in each one of these boxes, the equations we use today would be different, but the thing which governs the whole thing would be the same.
Speak up. Speak up.
Yeah. Yeah, exactly. Yeah, that's a good point. There are these long periods when nothing happens. Well, when I say nothing happens, the molecules move around, but they just look like random thermal equilibrium. They last for enormously long times, but nothing happens. So if you use some kind of clock which is not geared to the time, the microscopic time of the motion of particles, which is geared to things happening, practically no time takes place over that course of. So it depends on how you keep time. If you keep time by events which happen and change the system from one time to another. Nothing happens during those periods. It's a tiny, tiny time. If you follow each molecule and ask how many times it actually is banged into everyone, it's a huge amount of time. So. It's the first time I've ever been on Twitter.
This is from Bill Moyer, and he is wondering...
Bill Moyer. Bill Moyer? Whom?
Phil Moyer.
Phil Moyer. Not Bill Moyers.
He's asking, what is the approximate fractal dimension of the universe?
Oh, well, that depends on how big a scale you look at. Fractal dimensions are always things which depend on scale. I don't know what it is on the super microscopic scale. Some people think it's 2. I don't really understand why. They might not even be meaningful on super microscopic scales. On our scale, I know exactly what it is. It's 3 dimensions of space, 1 dimension of time. There's no question of that. On very small distances, it might be larger. The string theorists think the universe has more dimensions at small distances. At very, very large distances, this fractal flow does have a concept of dimension associated with it, but it's an odd concept of dimension, Hausdorff dimension. The Hausdorff dimension can be fractions and be irrational numbers, and it would be irrational numbers here. Typically less than 3, I think.
In this universe, are all constant,
The speed of light, it doesn't make sense to ask whether it's constant. It is the speed of light. How fast does light go? It goes as fast as light goes. That's another way of saying that the speed of light has dimensions. The right thing to ask about is dimensionless things. All right. So you could ask, for example, what's the ratio of the speed of light to the speed of gravitons? That, as far as we know, is exactly 1 everywhere in the universe throughout. You could ask the so-called fine structure constant. That's a dimensionless constant which has to do with the probability that if an electric charge accelerates, that it radiates a particle, that it radiates a photon. That's a dimensionless number. You could ask whether that's the same everywhere, and you could ask whether it depends on time. Now, as far as we know, it does not depend on time in our bubble. There's no evidence whatever that it depends on time in our bubble. In this kind of picture, it would make sudden jumps every time the bubble changed. It would make sudden jumps, and we have no evidence against that. We have no evidence against sudden jumps in it. We do have evidence against gradual changes over long, long periods of time in our bubble, in our world. So we have never experienced any evidence for a time dependence of what we normally call the constants of nature, at least at the moment.
It's getting late. Then you not have dinner yet.
What Jeffrey was really saying is that he's getting tired.
Welcome to everybody. My name is Jeffrey West, and I'm on the faculty of the Santa Fe Institute, and it's my real honor and distinction to be able to introduce our wonderful speaker tonight, Leonard Susskind. I've known Lenny for more years than I care to think, probably, and likewise, no doubt. And, well, I'll respond to that in a moment. We tried very hard to bring provocative, challenging thinkers that are kind of, pushing the frontiers and working on the edge. And there are very few thinkers in today's world more on the edge, in more ways than one, probably, than our speaker tonight. Lenny is a distinguished theoretical physicist who has made innumerable fundamental contributions to the field of fundamental physics, may be identified as a high-energy physicist or an elementary particle physicist or just a fundamental physicist working on fundamental issues in physics, conceptual issues, and tonight's subject is obviously quintessentially one of those. And Lenny is maybe best known of all the many things that he has done sort of in the public eye for, on the one hand, being one of the inventors, so to speak, of string theory, the idea that the fundamental forces, the fundamental objects, so to speak, of nature are not little Newtonian-like point particles, but are more little vibrating strings, and everything around us comes from the geometry and dynamics of the vibrational modes of those strings and the way they interact and so forth. He was one of the founders of that whole idea and has been instrumental in developing it. But also he's known for a dispute that he had with Stephen Hawking about the role of information and black holes, that the idea that black holes swallow everything up, including all information. This was a major dispute which lasted for, I don't know, 20 years probably, in which Lenny eventually was declared the winner. And this is no mean achievement, and indeed Lenny wrote a popular book on the subject, for which I think you got a prize for that one, actually, a book prize for that. So he's not only delved into the depths and fundamentals of physics, but he's also been a popular writer and written best-selling science books into the bargain. So, as I said, I've known Lenny for a very long time, for probably 40 years, and one of our disputes, mini disputes, is to do with time. Because every time we meet, Lenny thinks that I'm older than he. He knows in the beginning, he knows that when we first met, that I was younger than he. And so he has, as you will see tonight, a very interesting ideas about the concepts of time,